So as Terence just mentioned, today I just gonna be presenting some of our ongoing progress on 3D characterization of apple trees, especially their architecture in the orchard directly, with the hope we can get the new denominator from all these measures so that we can better estimate the crop load to make some adjustment in the measurement side. So just for your information, right? As an engineer, I kind of learned this tool all the way along with this project, and this is the current best practice for growers to really measure some of these architectural trees that can be used as the denominator, as what parents just explained. For example, the cross-sectional area or cross the diameter of the branches, and they use this kind of disk with different, predefined diameters so that you can easily just fit it in and then get an estimated number. So remember, this is not a direct, per decimal points, millimeter measurements. It just to give you some predefined, millimeter level accuracy of the branch diameter. So with all these, measurements, then many of the horticulturists could use those measurements to build the models to guide the pruning practices, or form different of the models that can be used to estimate the optimal crop load in the production side. But we all know this is very tedious. And even though we have this kind of a predefined parameters or diameter range, in reality, many growers won't really use them because it's tedious, take a lot of labor effort. And of course, now labor cost is the highest part, at least for the US, especially crop industry. So that kind of motivates us as engineers to develop new methodology so that we can automate this part and also provide better accuracy in terms of the accuracy. So since start of this project, we continuously scan the orchard in both Geneva and Ithaca, and some of these, commercial apple orchards around upstate New York, try to get their 3D point clouds using the state-of-art laser scanner we can purchase from the market. This is very important actually, because those scanners are typically designed and used for construction purposes, like what we kind of use from the Faro company. It's a Germany manufacturer, and each of these laser scanner costs around $50,000 to even some higher end close to $100,000. So it's very expensive, but of course, they provide the best accuracy. So these are some of the demonstration, point clouds we get from this laser scanner. As you can see, not only we kind of get very high resolution there, but also when you zoom in, you will be able to see all the details around each tree, right? As we discussed, our goal here is not only to measure the trunk diameter, but also the total branch length as well as their branch diameters so that we can form different types of denominators that can be used to estimate the optimal bud number or fruit number per tree. And with this thing, the first effort from my lab is to how to automate the whole analytical part so that once we get this, very high resolution and accurate, point clouds, how we can extract those trees we are kind of interested in or being useful for the horticulture management practices. So in the past kind of 2 years, we built this first 3D processing pipeline, try to characterize the tree architectural trees automatically. So on the top chart, you see that the entire apple tree we collected from the 3D point clouds. And then we have a segmentation algorithm that can identify each individual trees. You can actually see through their color codes. Different color means a different tree. So once we identify individual tree, now we will be able to first calculate the tree skeleton, right? Because we need to first know which part represents the trunk, which part represent, different levels of branches from primary to tertiary in this case. And once we finish that skeletonization, we segment each individual, branches from the trunk so that we can really enable the measurement of all different levels of architectural tree. For example, for the tree level, we measure the total tree height, we measure the trunk diameter, and then at the branch level, we will measure their radius or diameter, and we also will measure their angle with respect to their parent branches. And in this case, if we target for primary branches, their parent branch will be the trunk itself. So by using this whole pipeline, we will be able to characterize all those trees in the orchard very accurately. So here are some of the examples we analyzed for 2 orchards in the past 2 years. One is a kind of very mature orchards in Cornell orchards in Africa. Their growth year is around 15 to 20 years. And we also have some like a very young tree in Geneva in a breeding program, and they are about 2 to 5 years range. So from the diagram here, what we can quickly scratch is, so first for trunk diameter, tree height, all these tree level trees, we can provide very accurate measurements, especially if you look at the correlation value between the computer vision based estimation versus the manual measurements. The coefficient is 1, right, or close to 1. So that means all the measured trees can be directly used for our management practices or the modeling purpose. Although the correlation, always vary because you have different, data quality issues there. But in general, I think this is pretty accurate. And then when we look at the branch level, right, the first thing is actually the branch diameter. As you can see, it's not a surprise. The computer vision based measurements is somehow underestimate the branch diameter. And also when you look at the correlation is kind of a decrease significantly as compared with the tree level. So there are 2 kind of possible reasons there. First, as compared with the trunk, which is very obvious in the images here, right? You can already see that. So very likely we get all the surface points around that trunk. And then when you try to measure or estimate the trunk diameter, you have a pretty good constraint there to really accurately measure the number there. But when you look at all those branches, they're actually very thin. And that's where occlusion occurred very severely, especially in the 3D space, right? So you cannot really scan, the tree from all 360 degrees because the setup in the orchard itself. So that will sometimes cause the missing data points. And once you have those missing data points, and that really represent the branch diameter, that's where you lose the accuracy there, because we have to use some interpolation method, try to estimate rather than measurement. In addition to that, actually, many of those, tree branches are pretty small. As you can see here, even from the manual measurement range, right? So their diameter, their whole kind of diameter is around, 1 centimeter each. As compared with some of the well-established methods in forestry, right, where the branch diameter is usually being, at least a 2 to 4 centimeter range, you see a substantial decrease there, right? And that requires a higher accuracy from the measurement from the imaging device itself. If your imaging device being limited to, for example, only 5 millimeter precision or accuracy, and then you probably will kind of gain the error at the beginning of your data collection part rather than the analytics thing. So that's kind of the thing we are working, try to address. Later on, you will see in the later slides about that. So then next for the branch inclination angle, we actually get a pretty decent measurement. And as you can see there, the kind of coefficient is also, the slope is also close to 1, which means the measurement from our algorithm can be directly used for the downstream applications. But of course, angle is very tricky, especially when you try to define it from the 3D space. Sometimes even we use the angular rulers, sometimes it's just really hard to project the two branches onto the same plane that forms the angle we are looking for, right? Because that's really not a simple 2D. But I think from that perspective, considering all the potential measurement challenges from the manual measurement part, the accuracy is actually pretty good. But we know branch angle may be less important for forming the denominator for crop load management. So how are we gonna be able to increase the accuracy for branch diameter measurement is the kind of a key question here. So then what we propose is that if the raw data quality is the kind of hinder for the whole process, why not we just fix that before we really analyze the tree? So what we propose is first we're gonna have the 3D-point clouds of those trees, and then we segment them into kind of a very short linear units. We call them LU. So with that, we can have a pretty good assumption because the branches are generally cylinder shape. And if they are in a short segment, we could just estimate that by using some like a cylinder fitting models. And then with that, we could use some learning-based method to fill in the missing point with the hope by filling in those missing points, we can actually get better estimation or measurement for the branch diameter. And then we put all the branches back together and form the final tree there. And that's kind of the tree we after the kind of missing points completion. So as you can see, even you look up closer, right? Even you still have some like missing points there, but that's largely just not being acquired by the laser scanner anyhow. But anything else, if they are not kind of a cylinder at the beginning, now they look just as cylinder. So we use the improved point clouds to run through the analysis again. And what we found is first, if you compare the correlation analysis, the slope coefficient is much closer to 1, which means the measurements could be directly used as opposed to we create some like correction factors. Well, that might be a kind of a quick workaround solution, but sometimes try to find a proper correcting factor takes a lot of effort, and we know that could be very likely site-specific, which is not ideal for commercial purposes. And second is, even though the correlation looks a little bit lower than before we filling in those missing points, but if you look at the absolute measurement error and RMSE, they drop significantly. And since our interest is how accurate we can measure the actual diameter to form the denominator, that actually tells us, yes, we somehow really achieved that goal. But of course, why we call those decreasing correlation is because of the I would say outliers there, as you can see from the two red circles there. So first, as I mentioned, some of the branches diameters is just really small. And how to deal with that is almost like how we deal with the long tailor problem, say in flower detection, right? You always have some like smaller, tiny things that your model won't be picked up very accurately. So we are kind of addressing that right now. And sometimes we feel it's more related to where we really measure the branch diameter. So we kind of communicated with horticulturists and we define, around 5 centimeters away from the joint points between the primary branch and their trunk. But sometimes, first, we could still have missing points around that segment because of the occlusion issue. Second is sometimes the very beginning of the branch could also be curved. And then once you have that curved part, it's really hard to define which cross-sectional part should be used to measure the diameter. So I think this takes more effort, in collaboration between engineers and horticulturists to better define those morphological trees so that we can have a better solution. But in general, I think we are heading to the right direction to really improve the measurement accuracy for branch diameter so that we can, generate different denominators for crop load estimation. So in terms of the next step, the first thing is this pipeline is well established. and fully runnable. And I will be working with Terrence in this year to use one of his trials to mirror all the tree architectural trees, and also to manually adjust the crop load with the hope to establish the relationships between these two parameters, or a set of architectural trees versus the optimal crop load. So if we can achieve that, I think then ultimately is a key question for many of our industrial partners here, whether or not you are willing to work with us either to commercialize this part or to develop different 3D imaging technologies to estimate the architectural trees, because they would have great value for crop load management. And second is to develop a joint learning system for both 3D reconstruction and analysis for apple trees. So with regard to that, just to give you some quick ideas. One thing is to form a digital twin for apple orchards. So as you see there, so all the trees are actually from Terrence orchards right now. And then we will be able to use some generative AI models to create new tree architectures based on the current tree architecture, and then put them back in a simulation environment. And then sometimes for these cracking factors, instead of doing extensive tests in the field, we probably will be able to do that in the simulation tool and to generalize to different sites. But of course, this is a kind of an open collaboration opportunity between academia and industry. And second is actually what we are trying to use for pure vision-based solution for 3D reconstruction. So as I just mentioned, we already use the state-of-art 3D laser scanner. So we probably don't have much room from the hardware perspective to further improve the imaging quality. So we have to use new methodology to really enhance the 3D point cloud data quality, so that we can simplify many of the analytics part. So one of the kind of very promising direction in AI space is that we can use neural implicit representation, or specifically neural radiance field or neural span distance function to represent the 3D architecture of any objects. And now we we are doing some preliminary tests to using different methodology, mirror all those tree architectures. And here are 4 demonstrable videos you can see. Faro is the data from the most expensive hardware, but for the rest of the 3 are from just a cell phone taken images. So if we will already use your imaging system to do the crop load estimation, I think then it would be a great opportunity for us to collaborate together to find a new way that can convert all those 2D images into this high quality 3D representation that will not be able to mirror the tree architectural trees, but maybe another possibility is we can map the location of all those trees, right? Because in my opinion, the information we provided here is valuable already, but also can have potentially more value to the growers. Like, for example, how these maps can be conveyed back to the sprayer technologies, or even the robotic harvesters, robotic pruners, so that all this information can be directly used rather than they reinvent the wheel on their own system. So in my opinion, that really definitely gonna help the whole industry to move forward much faster than what we have right now. So with that, I would like to thanks for your attention to my slides. I guess perhaps I will just receive some questions at the end of the whole engineering presentation section.